So topic 4 is the binary dependent variable. Okay, so this is the binary dependent variable model. And this model is used when my dependent variable, let's call our dependent variable y, is equal to beta naught plus beta 1 x1 plus beta 2. I'm just going to make a simple model. x2 plus ui, and we have the sub I everywhere. And this model has y binary, meaning it takes 1 or 0. That's it. It's not continuous. So everything that we have been doing so far since the beginning of the semester, we used to have y as a continuous variable. Now y is a binary variable. Y binary variable, like a dummy variable, can take only just 2 values, 1 and 0. I really don't care about the values of x1 and x2 or x3 or xk. They can be like continuous and they can be binary as well. I really don't care. Okay, so what we care about in this topic is the dependent variable. Okay, so when I have the dependent variable just taking values of 1s and 0s, then I cannot just estimate it using the just regular estimation methodology. So we have 3 main estimation methodologies. So the 3 main estimation methodologies are, number 1, linear dependent, sorry, it's not dependent, it's a linear probability model. So it's linear probability model. This is like the very old type of model. And people have found so many disadvantages with this model, so they have invented 2 other models, the probit model and the Logit model. So as I said, this one has many disadvantages. I'm going to go over these, and I'm going to cover this model as well. But I just want to let you know that currently, whenever we have a binary dependent variable, we either choose to use either probit or Logit. And back in the past, before the invention of computers, people used to do these models by hand. And it was the case that the Logit model was much easier to do by hand than the probit model. And now with the invention of statistical softwares, it's just indifferent. They would give you like very, very close results. Okay? Can you see and everything is fine? Can you type? Just let me know. Perfect, thank you. All right, perfect. So let's start with, like our lecture today is going to be, we're gonna start with the LPM. Linear probability model is abbreviated as LPM. I don't really like it, but I'm going to cover it. And then we're going to talk about the probit and the Logit. And the good news is on my channel, on my YouTube channel, you would have also another, like you can just watch it and you're going to have another explanation. So let's start with the first one, linear probability model. So I do have a model in which, for example, or in general, y can be 1, for example, if the person owns a house. And so it's going to take 1. And it's going to take 0, which is the other outcome, if not. You can have a y 1 if I graduate in May. I'm sorry, if whatever you can hear now is my neighbor upstairs. He decided to make his apartment as his gym, which is fine for me. Given the current situation, like it's okay, but anyways, I'm just letting you know. So it's a graduate or not, or you can take 1 if you find a job, right? Or not. So this is exactly what we are trying to do in this topic, okay? So let's see, linear probability model is again an outcome and a probability. So if I have, for example, y equal beta 1 plus beta 2 xi plus ui, and suppose that x equal family income, okay, and y is going to take 1 if this family owns a house, and 0 if not, okay? So I'm trying to see a continuous variable, because family income is in dollars, a continuous variable on a binary dependent variable, okay? So I want you to understand that what we're trying to do is we're trying to compute the expectation of yi given certain level of x equal small value. So this is just a notation, okay? So I'm trying to find the expectation of owning a house given income is equal to a certain value. This is exactly what you want to do, okay? And given that y only takes values from 1 and 0, then the number I would get, like my y hat, is expected to be between 0 and 1, just like a probability, right? So what we're trying to do here is we're trying to find an estimation for y that is a number between 0 and 1, and we call it, in statistics or in general, we call it a probability. So in order to compute this expectation, we know from statistics that expectation, what is this? Just a second. So we know that, I'm sure that you remember this, the expectation is equal to an outcome times a probability. Anytime I just want to compute an expectation, then I need an outcome. My outcome here could be like 1 or 0. And I need a probability attached to being 1, and I need another probability attached to being 0. So let's assume that the probability that yi is equal to 1 has a probability called pi, and that the probability that yi is equal to 0 has a probability of 1 minus, which is the left, 1 minus pi, right? So this is our assumption. This is what we have. So if I want to compute the expectation, I need an outcome times a probability. An outcome times a probability plus an outcome, second outcome, times its attached probability. So my expectation of yi given xi is equal to we can write it in this way, pi times 1 plus 1 minus pi times 0, right? And then this part is times 0, then it's cancelled. This is times 1, then it's simply pi. So my expectation of yi given xi is equal to pi. Okay, so we can, are you done with writing? Let me just make sure, done? Okay, fine. All right. So we can be more specific about this part, right? And say that, so I can either write it this way, my expectation of yi given xi is equal to pi. Sorry, this is equal. I missed the equal and it's too tight here. So let me make more space. So is equal to pi, okay, Or I can be more specific and more accurate and say my expectation of yi being equal to 1, or it appears, or I own the house, given a certain amount of income, is equal to the probability pi. Okay? It's very important to notice that this expectation of yi given xi, again, you can write it either this way or this way. Okay, so let me write it this way. Is always between 0 and 1. It's a probability. So I'm going to get by the end a certain probability. Okay, so let's see how the linear probability model works. The linear probability model is simply estimating the model using OLS, or in Stata, you just type regress, same as we did. Okay, so it's going to be like regress y x, let's say z. Okay, so I suppose I have two regressors, x and z. So it's just going to be like an OLS model. And in my example, okay, let me write the example in the next page. Are you done with this page? Okay, I'm going to add. Okay, so I just want to write the example in one slide. So the example is, I just estimated it using my OLS regress command. So yi hat is equal to minus, I'm just giving you an example. So when you ask me where did you get these numbers, it's just an example using family income and the probability of owning a house. And these numbers I got after I run the model, plus 0.1021 xi, and remember this is the family income, and remember this is probability of owning the house. Okay, and we have a standard error as we usually do, like it's right under each coefficient, and we have the standard error right here. I really don't need it now, but just for completion, I'm just gonna have it. You have R squared, 0.8, and so on. How can I interpret this model? This is a linear probability model. This is exactly what we have done before, nothing new until now. Okay, so the linear probability model is simply estimating the model using OLS. Okay, so how can I interpret this model? So this one gives me the probability that a family with, you know this already, 0 income owns a house, right? So this is, you know already. Since this probability can never, like, this number is negative 0.9457. What can I tell about a probability that is negative? The LPM treats the value, or treats this value as 0. So in the number line, this is the 0, this is the positive side, this is the negative side. So any number that is right on the negative side, the LPM treats it as probability of 0. And this one would be read like, the probability that a family with 0 income owns a house is simply equal to 0 probability. Okay, and this is how the LPM works. Okay, again, this is the disadvantage because we never expect a probability to be equal to negative, but if it does, LPM would say, okay, fine, this one is 0. Next, let's talk about the partial slope. Let me erase this part so that I don't want to be like, I want to be on the same slide. So I hope that you will write right after me, because I don't want you to miss anything. Anyways, the video will be recorded and on coursework. So if you missed anything, you can just go back and repeat. What about the partial slope, the 0 1021 basically means that a unit change in income. And I want to let you know that here the unit, this one is measured in thousands of dollars. I should have told you this. So this is measured in thousands of dollars, okay? The variable income is measured in thousands of dollars. So when I say unit, then a unit is a 1,000 increase or a 1,000 decrease. It's a change, okay? So a 1 unit change in income implies, you can multiply this times 100, 10.21% probability of owning a house. Okay, so you take this number and you multiply it times 100. It's a fraction between 0 and 1. So to read it nicely, but just better to multiply it times 100 and say, let me say instead of change, let me say increase, because it's like usually when I ask you about, sorry, when I ask you about a question, where's this? When I ask you about the question, I usually ask you about a unit increase or decrease, okay? So a 1 unit increase in income implies 10.21% probability of owning a house, okay? So I can also use this model to ask you questions. So let's see. So what if, I don't know, the eraser doesn't work for some reason. The small one doesn't work. We have different sizes. So what about the probability of owning a house at income equal 12? And remember, everything is measured in 1,000 units. So when I ask you about what is the probability of owning a house if the family has $12, this is exactly the same as or 12,000, because the unit of measurement is in thousands. Okay, so now I want to compute this. I'm going to say, okay, I'm going to plug in this number in y I hat, and I'm going to say, okay, y I hat is equal to negative 0.9457 plus 0.1021 times 12. Okay, you just multiply and add and subtract and whatever, and then you will get this number, 2795. What does that mean? A family with 12,000 income has, let me write here, has a probability of 27.95% of owning a house. Okay? Clear? Yes? No? Okay. If you have any questions, just type on the discussion forum. I mean, not discussion forum, the chat. I have it open here. So what I see is yes, 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 which means it's clear, which is perfect. Any question, just type it here and then I'll stop and answer your question. Okay, so let's use the same model and say, okay, what about at income equal 1 or 1,000? What about at income equal 24, which is 24,000? Compute the probability. So here I'm going to compute the probability and say, okay, y I hat is equal, you just plug in the number again. Let me just make sure I'm writing it here one time, and then after that I'm like, if it is not clear, then you let me know. Times 1, and the number that you will get is this is negative here. The number that you will get is unfortunately negative 0.84, and for this one the y I hat is equal to negative 0.9457 plus 0.1021 times 24, and the number that you will get is 1.5. Now this would brings us to the main disadvantage of a linear probability model. What I see here is a probability that is negative. What I see here is a probability that is exceeding 1. We couldn't see it here in the previous question. It was like a number in between, right? Which was okay, between 0 and 1, which is fine. But extreme values would introduce these crazy numbers, okay? And this was the main disadvantage of using linear probability model, is that the expectation of yi given xi will not always be between 0 and 1. Okay, so this is like a disadvantage. We always understand that probability is only between 0 and 1. And actually, when you check how it looks in the graph, so you have this axis has own house, and then you have on the x-axis you have income, and we're trying to figure out how income affects the probability. It's a probability, so it's between 0 and 1. Okay, my observations, the one that I get would be like here, there, right? We don't expect any numbers in between, right? And these are the observations that we call the population observations, or the observations that we actually get before we start estimating the model. Now, after estimating the model, we're probably gonna get like something that's not probably like based here. This is a negative intercept. So the intercept starts from the negative part. Let's say this is 0.94, whatever the number, and then has a positive slope like this, okay? So the main disadvantage of the linear probability model is I would have numbers above 1, numbers below 0, numbers above 1 and numbers below 0, okay? So this again creates problems, because according to the linear probability model, when you give me a negative number, I'm gonna say, okay, this is 0. When you give me a number that is above 1, I'm gonna say, okay, this is a probability of 1, okay? So it's not that accurate. The other problem about the linear probability model is as you can see, it's a straight line, right? The name actually say linear, right? Probability model. So it's a linear, so it's a straight line. This straight line cannot capture all the points, right? So anything that is here, I don't have actually any observations here, right? Using R square would be like meaningless, because the R square is supposed to measure the distance between each observation and the estimation line. So this is a huge error right here, right? And then also here, what about this one? There's a huge error. The distance here is small, so okay, I'm fine here. But other than that, I cannot use the R square or the adjusted R square because the dependent variable is binary. Okay, so anytime I have a dependent variable that is binary, I cannot just go ahead and keep using the adjusted R square or the R square, because it would give me meaningless results. The line itself is passing in an empty area, right? I don't have any observations right here. Other than that, we just use the same way that we used to do, meaning I interpret the intercept the way I used to interpret it, the sign, the partial slope. I can also use these two to compute the t-statistic, right? It's exactly the same way that we have done before. I can use these two to get the p-value. I can use these two, when I say these two, the coefficient and its standard error, to compute the confidence interval. Like everything proceeds the same way that we used to do. To address the problem of probability exceeding 1 and being lower than 0, there are two other models introduced. So the probit model is one of the ways that is used, I'm sorry, Probit model is one of the ways that is used in order to overcome the problems that we have with the linear probability model. Like when you ask me, no, not so many people now use linear probability model, although you would find it in some research papers. So the linear probability model is, we actually have the same story, okay? So now again, I would like to compute the expectation of y, same way, given x, I. So this is a square bracket, okay? So it's the same thing. Or I can be more specific and say it's the expectation of yi being equal to 1 given xi. Again, you can either use this or this, it's the same. Any expectation is outcome, so it's either 1 and 0 times the probability, right? My probability before was pi 1 minus pi, okay? So I would multiply, add, okay? Now, the main difference between the Probit model and the LPM is that now my probability is not just going to be our simple probability, the one that we know. We're going to change the probability using the cumulative distribution function, or the Z, you know, the Z table that you actually been using for the p-value. So the main change, I'm gonna erase this to, now the eraser is working, perfect. Okay, so the main difference is that now with this Probit model is this one has a cumulative distribution function that takes this notation, which is, we call it phi z. Okay, so instead of p, whenever you see p in the previous slides, you just type phi z, or 1 minus phi z. And phi z here is the cumulative, I'm sorry, this is too slippery, the iPad, distribution function. Okay, so the cumulative distribution function, we call it the CDF. This is actually the one that you call it the Z table. This is actually the one that you use it for the p-value, the one that you know. Okay, so it's nothing new. That means we actually need to go to the table and find these probabilities. I'm going to show you this later. So now what I need to do is just replacing each probability with the phi z, right? So I'm going to just, again, repeat whatever I've done. I'm just going to compute this. Expectation of yi given xi is equal to the probability, right? So each one has an outcome times phi z, right? Plus 0 times 1 minus phi z, right? Let's put these in a big bracket so that we're not confused. Actually, this is 0, it's gone. This is 1, then it's actually equal to phi z. Okay, so how can I apply this to my example? I just want to let you know that this phi z, whatever this, you know this already. Like we used to say z is just a number, right? So whatever I have z here, z actually here has everything that beta naught plus beta 1 x1. And these are the estimated, okay? And you can actually have plus 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 beta hat k x k, all right? So let me show you in the same example. So in this same example, let's just continue with the example that we have. So again, suppose that I have the same example, family income, each unit is in $1,000. So my probability now is equal to, my new probability is now phi of z which is beta 1 plus beta 2 xi, where xi is the family income, and these has the hats because I don't have the error term here. So in other words, my yi hat is equal to phi of negative 0.9457 plus 0.1021 xi. So if I ask you, what is the probability of owning a house at income equal 1 or 1,000? Okay, so the unit of measurement is 1,000. All what I need to do is just plug in the 1 right here, right? So yi hat is equal to this phi symbol, negative 0.9457 plus, just multiply and add, and you already have this number from, right? We already have, I'm just going to show you. Okay, it's right here, this number, using the same number. Okay, so this one is actually, this number is now inside the cumulative distribution function. Okay, that's why it's nonlinear. If I just leave it by itself, then it's linear, but now it's inside a function that is nonlinear. Okay, so I want you to understand that I'm looking for the cumulative distribution function, which is the bell-shaped distribution, right? It's a bell-shaped distribution, and I'm looking at the shaded region under the graph for all the points that are less or equal to negative 0.84. I'm actually looking at this probability. So what you need to do is you need to go to the z-table, right? The same way that we used to find the p-value, and you need to find, and just remember that this is also can be written as 1 minus phi of the positive part, right? It's exactly the same. So this is just, or it's an additional step. You can forget about this step. I'm just letting you know that there are 2 ways of writing the probability. Now you just go to the table, and let me just erase this last part. I just wanted to give you additional information. Okay, so I'm just letting you know that you can either do it with the negative part or the positive part. So now when you go to the table, you will find this number equal to 0.2005. Multiply this times 100, then you can write your conclusion. At income equal to 1, the probability of owning a house is equal to 20.05%, or there is a 20.05% probability of owning a house given the income is equal to 1,000. Is this clear? Yes, 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 yes. Perfect, thank you. All right, again, any question, let me know. So as I'm letting you know, this is a very simple example, just 1x, but we can actually expand this model, right? We can just expand this model, and you can see my YouTube video has like an expanded version of this model where I have these keep, like, basically keep going up to, I think I have 6 or 7. Okay, 6 or 7 variables. All what you need to do is just plug in the numbers, and you go to your z table, the one that you know, and you just get your probability, multiply it times 100, and you get the answer. Okay, so let's do something else. So suppose that I'm asking you this question. What is the effect on the probability of owning a house given income changed from 1,000 to 2,000? Okay, I want to compute this one, the change in the probability of y being equal to 1 given the change in x. So you just like take the words and just write them into notations. This is going to be equal to phi of beta 0 plus beta 1, 2, right? Minus phi of beta 0 plus beta 1, 1. This is exactly what you need to do. You just plug in the numbers that we have for beta 0 and beta 1. So equal to negative 0.9457 plus 0.1021 minus phi of, remember this number that we got from the previous slide, right? So when I plugged in 1 here, I got this number, so I'm not going to repeat it. So I'm going to take this number right back here. So this one is negative 0.84, okay? And then again, all what you need to do is, so this number, when you add and subtract, you will get it as negative 0.7415, okay? So now what you need to do is you go to the table and you find this number as 0.2266 minus 0.2005 equal to 0.0261, and you say, okay, you answer this question by saying the increase in income from 1,000 to 2,000 implies 2.61% probability, or 2.61 increase in the probability of owning a house. Okay, so I think it's like it's not too challenging. So this is a very again simple example. The probit model always takes an S shape, so that's why it's non-linear. So just like this, I'm going to write it here. So I have numbers that are between 0 and 1. It never falls below 0. It never take any value above 1. So if my observations are here and here, then this probit model takes an S shape. Doesn't never above 1. So it takes an S shape. Okay, and this is a great advantage over the linear probability model. We don't have any problem of anything here or anything below the 0. So it's just like normal, right? Values between 0 and 1 in this interval. Okay. So the next one, which is the Logit model. The Logit model is a model, has the same advantages of the probit. So the Logit model, again, overcomes the problem of the linear probability model, where you compute a nonlinear function that never goes beyond 1 and never falls below 0. However, this one has the main difference is that it's actually very similar to probit. People used to love this one, used to use this one before the invention of Stata and other statistical softwares. This one was much easier. And I'm saying it's similar, but the only thing is, instead of using the cumulative distribution function for calculating the probabilities, this method uses the cumulative logistic function. Cumulative logistic function, CLF. Okay, the cumulative logistic function. And actually, when you think about it, what is a cumulative logistic function? It has this notation. So now my probability that y is equal to 1 given x, you can make it like x1, x2, just make it like more general. Okay, xk is equal to the cumulative logistic function takes a notation of f, like the cumulative distribution we used to say phi, right? The logistic one takes an f. Okay, it's just a notation. It has nothing to do with the f distribution or anything like that. Okay, so it's just a notation f. Beta naught plus beta 1 x1 plus beta k xk. And if I'm saying these are estimators, hats, and it's equal to 1 over 1 plus the exponential function of negative beta naught plus beta 1 x1 plus beta k xk. All these has hats. And as you can see from this formula, I don't even need to use theta, right? I just need an exponential function. If I have my calculator, I can compute the logistic function because all I need to do is an exponential, just plug in these values into an exponential function. And that's why people used to prefer this method because it actually doesn't require any complicated computations. Okay, now, like nowadays, there is no preference between the probit and the logit because they are equally easy in computing, given that we have just Stata. So all what you need to do is just change the command in Stata and you will get the results. Okay, but if you're doing it by hand, then definitely by hand, this one is much, much easier. So let's take the same example. So same example, okay? Again, this is a very simple example. So, okay, what is the effect on the probability of owning a house if, okay, if income increases from 1 to 2, 1,000 to 2,000. Okay. Now, before I do that, just, I'm sorry, I should have written this in the previous slide. I'm sorry, let me go back here and write this here. So the expectation of yi being equal to 1, right? Okay, equal to 1, given xi is equal to, I have a probability and I have outcome, right? My outcome is 1 times a probability, we call it f of z. So whatever here, just call it z, just for simplicity, okay? Plus the second outcome 0 times 1 minus f of z. So we're just repeating, anywhere I see phi, I just replace it with f. This part is gone because it's times 0. This one is times 1. So the expectation, just repeat this part, is equal to f of z. Okay, so when I want to compute or when I want to answer the example, so what is the expectation of yi equal to 1 given income is equal to 1? I already know the number, right? So we got the number here. Again, I'm reminding you, it's this number. Instead of being inside the phi, now we put it inside the f. So it's equal to f minus 0.84, which is equal to 1 over 1 plus e to the power negative. It's in the formula, has negative, minus 0.84. So don't forget the negative, okay? And this one is equal to, we just compute this one, 0.3015. So at income of 1,000, the probability is equal to 30.15%. This is at income 1. What about at income 2? So when income is equal to 2, you just repeat, and the expectation of yi equal to 1, meaning owning the house, given income is equal to 2,000, is equal to 1 over 1 plus e minus 0.7415, right? Just computed by the calculator, and then you will find that 0.32267, or at income of 2,000, the probability of owning the house is about 32.27%. Now, to answer the question, if income moves from, if the income increases, the increase in income from 1,000 to 2,000, how this would affect my probability of owning the house, you just subtract 32, or let's write it in fractions, 3267 minus 0.3015. We will get this number as 0.21111. Okay, 11. Okay, and so you can say this implies there is a 2.11% increase in probability of owning a house if the income increases from 1,000 to 2,000. Okay, so it's again very similar to the linear, to the probit model. The only difference is we are using different probability. In terms of the graph is actually the same, an S shape. Okay, so again, I'm sorry, I'm writing it here, just trying to, instead of going to the next slide, in case you haven't finished writing. So 0, 1, again, my observations are always between 0 and 1 for the Y. And the probit model, we said I have an S shape for the probit. So suppose this is the probit. The Logit model is actually very similar. It starts a little bit higher, right? And then it intersects, and then it's getting lower. So, sorry, this is the Logit. Okay, so this is the Logit. Okay, so the difference between the two is very, very, very small. Usually, like in practice, let's say if you're using this for your project or any research paper, and your Y is binary, then you have the choice between the two options. They would give you very, very similar results. Okay, clear? Okay, good. All right. So there are important things I want to mention about the 3 types, or I mean like the 3 methodologies used. So we have covered the linear probability model, the probit model, the Logit model, and the main conclusions, I would say. Let me write with the white. So the main conclusions. Number 1, I already mentioned that. So LPM cannot capture all the non-linear nature of the let me write it of the y or of the true population parameter. Okay, so it doesn't like take all the nonlinearity of the y, it can't capture it. And we also said the probabilities might exceed 1 and might fall below 0. Okay, so we have seen an example where this one is 1.5, and if it is 1.5, they treat it as 1. We have seen an example that negative 0.84, and they treat it as 0. Okay, number 2, probit and logit, both they produce actually similar results. Okay, so use whatever you like if the question doesn't tell you which one to use. Okay, similar results. You can pick again the one that you like. They capture the nonlinearity of the true population parameter. Okay, so that's why they are preferred. Okay. Next, number 3, and this is very, very important. If I have estimated the probit and the logit, so if I have the estimation results of a probit and a logit model, then I would have like the probability, let's say, I'm just again referring to the same example to make your life easy. So the probability of y, which is equal that the family own a house given certain level of income, we said it's equal to phi of beta hat naught plus beta hat 1 income. And the probability that y owns a house, or the family owns a house, given again income, using the logit function would be f of beta hat naught plus beta hat 1 income, again the same. It's very important to understand that this beta is not the same as this beta. This beta 1 by a function, and that's why we have to give them different names. So this one I'm going to call it P for probit, P1. This one I'm going to call it L0, L1. Okay. It's very, very important to notice the following. I cannot compare this intercept with this intercept. I cannot compare this partial slope with this partial slope. What I can compare is the outcome, which is the final result. Okay. Why? Because I'm actually, like, it's not fair, right? I have different parameters inside the function, and each one has a different function, cumulative distribution versus the cumulative logistic distribution. So what I can compare is just the values that I can get by the end. So we have to say that we cannot compare beta hat naught of the probit with beta hat naught from the logit. The same thing, I cannot compare their slopes with, this is L. Okay, because they are actually two different models. Okay, so this is L1. The only thing that you can compare the resulting probability. The resulting probability, which means I can compare the values that I get from here. I can compare the values that I can get from here. The other important thing to know or to understand is everything inside the bracket here or there has the same, it has the same interpretation, in the sense that I can see an intercept, I can see a slope, right? And I can see, of course, the sign. I can compute the t-statistic, so it's okay, you can compute the t-statistic because you will have a standard error. You can compute the p-value, you can compute the confidence interval, so everything as we have done before. The only thing that you really cannot do is you cannot use this coefficient and say, what happens if 1 unit increase in income, and I use this coefficient to interpret the probability? No, I have to do it the same way that we have done it here. So if I go back and I'm asking you, what is the effect of a change for a 1 unit, right? 1 to 2. What I need to do is to plug 1 time with the 2, 1 time with the 1, and compute the difference to get the resulting probability. I can never just look at here and say, okay, a 1 unit increase implies 10.21%. Why? Because it's inside a probability. Okay, so anytime I have a cumulative distribution function, whether this is probit or logit, anything that is inside the bracket, I cannot interpret the coefficients the same way as we used to do. I can never use the slope and say there is a 10.21% increase for 1 unit increase in income. In order to answer the effect of a 1 unit increase in income, I have to plug it into the function twice and get the difference. And it's going to be clear when you also see the example on my YouTube channel. Okay, so before I leave this, I just want to make sure that we are on the same page. Let me share with you the, where is it? Okay, so when you go to, okay, so when you go to my YouTube channel, I want you to, again, I'm sure, I know that many of you have watched this already because I can see the number. I want you to repeat, watch this again, okay? Number 1, you watch number 2 in that order, okay? So 1, 2, all right? And in number 2, I'm not going to show you everything. I just want to show you that here I have an expanded version of the model, okay? An expanded version where I have x1 and x2 and x3. And here I'm also trying to just show you where, okay, I'm giving you an example. This is very important. So example on your textbook, page 593 to 595, it's about the labor participation rate of females. 1, it takes 1 if the female participates in the labor force, 0 if not, and so many factors affecting the labor participation. We are focusing on the number of kids per female who are less than 6 years of age, okay? We want to see if the female has more than 1 child or there is an additional child in this age category, less than 6 years of age, how it affects the labor participation. So this example, I mean, like, this video is very important because it will like show you in the expanded version. I'm actually showing you a picture from the textbook, the page numbers I just mentioned, and I'm comparing the probit, the logit, and the linear probability model. And I'm letting you know, and this is very important, that we can never look at these coefficients and say anything about these variables. I cannot say education increases the probability of joining the labor force by 22.1%. I can never do that with a logit, and I can never do that with a probit because all these numbers are inside a function, inside a bracket, right? So you cannot just take these numbers and interpret them. You cannot, you can actually do that with the LPM because the LPM is just our OLS, Okay, so I want you to watch this video. It's 24 minutes, but it's very, very important. It's showing you again the S shape. It is called an S shape, but it's actually like a very flat S shape, and showing you an example. Also, I want you to, my internet connection is not that, okay, just a second. So I want you also to watch the video, which is very important, which is how to estimate in Stata, right? So when you estimate in Stata, I'm showing you again the same example, the one that you have on your textbook, okay? And the one that you have on your textbook, I'm just replicating it, showing you how you can estimate the model using the linear probability, the logit, the probit, and how can I display the results for a change, right? And then everything is held constant. One, this variable is held constant. This variable is held constant, same, no change, no change. This is the only change. So, and again, no change here. So when I ask you what is the effect of the increase in the number of kids less than 6 years of age, then I just need to have two equations. One before the change, one after the change. Again, this is the logit. All what you need to do is just instead of regress command, you have logit, and then you type the equation. And here I have a robust standard error. And then again, just copy paste whatever. And then you have here again, the same equation. Everything, as you can see, is held constant. The only change I'm focusing on is the number of kids. And this is, let's say, because the question was asking me to do that. And the difference would be the difference in when the value of this variable is equal to 1 versus 0, okay? And then you take the difference in probability and you display it. Okay, so I just wanted to make sure that, what else I want to show you?
Can I ask a question?
Yes, sure.
Are you changing anything about the way that the class is structured, like the assignments or the final exam or the project, just for like our future reference?
Yes, so what I'm going to do is send you a schedule, an updated schedule toward the end of this week. And in terms of assignment, we just have one more assignment and it's in the same date. Everything is exactly the same. The only thing I'm going to change is I'm going to delete one of the topics because we don't have time to cover everything. Okay, in terms of the project, I have already changed the date of the project, right? In terms of the submission of the first draft and the final draft.
And then the final is remaining the same, or are you going to be changing that?
The final exam?
Yes, sorry.
Yeah, the final exam is going to be the same. It's just going to be online. You know, I might give you like an additional time, but it's going to be basically the same.
Omitting that one chapter that we're not learning.
Yeah, exactly.
Right.
I just want to show you here that we have the lecture slides of this topic. You have an additional example that I want you to go over. The slides are very important. What I'm going to do, I don't think we will have time today. So what time is now? Oh, we're almost, we have, what, 7 minutes. Okay, I want you to go over the slides. These are 48 slides. We have simple examples, okay? And then towards the end, you have, and I'm showing you here in details how to get the value from the Z table. So it's very, very important to watch this, okay? I mean, like to study the slides. The other thing is there is a tomorrow recitation, virtual recitation. What I did is I have uploaded for you the data set, charity data set, whether the people participate in charity, respond to charity or not. And this is like a dummy variable. And you have a question here, which is just a, an unstated question. So you can, you will go over it with Qasim tomorrow or on Monday. So it's going to be repeated on Monday. And also we have the Stata question. Okay, I told him to start with this one first, Okay, so he will start with this one first, and then he will, if time permits, he will go over the non-Stata question.
Since we didn't have recitation this Monday, can you make available the video from last Friday's recitation?
I think, isn't it already available? No?
I couldn't find it personally.
Okay, so I'll make sure, yeah, sure, I'll make sure it's available, no problem. Okay, so where are we? Let me just, okay, so we're here. Okay, so the remaining parts of this topic is measures of fit. Okay, so the measures of fit that we know, like we know the adjusted R squared, the R squared, the root mean squared error, the F statistic, all these things. So whenever the dependent variable is different now, like we have a variable that takes 1 and 0, then we cannot just keep using the same measures of fit. So we have actually different measures of fit. So the ones, like there are many ones, I'm not sure if time permits, I'm going to cover them all next week. So we have count R square, okay? And then we have pseudo R square, okay? And then we have the McFadden. I'm just going to see if I'm going to give you this one or not. Okay, let me first give you something else, I'm sorry. I'm going to give you something else first. Okay, so we have, I'm just trying to make the same order as the order of measures of fit that you will find on my video. So the wall test, and then the likelihood ratio test, okay, and I think I'm going to stop here. So I'm going to give you like 4, okay? And if you watch my video, I started from, I think I started from here, okay? So why? Because as I said, like this video was actually recorded last semester for my students where I was in class. I mentioned 1, 2, and 3, and then I recorded for them number 4. So let me tell you what is a count R square. Actually, count R square is easy. The count R square, as the name suggests, you keep counting. Counting what? So let me show you. So the count R square is, let's say I have Y that takes, I know that it takes only 1s and 0s, right? So just an example. Okay, so this is an example. So suppose that the first observation is 1, the second is 1, 0, 1, 0. 1, 2, 3, 4, 5. I have 5 observations. I have estimated the model, and I suppose that my estimated Y hat was numbers that are 0.6, 0.1, 0.4, 0.3, 0.2. The count R square is actually going to go over each observation, and if the observation, or like if the number or the estimation that you get is 0.5, it's greater than 0.5 when Y is equal to 1, then the conclusion is correctly estimated. Okay, so here the Y is 1, the number is above 0.5, correctly estimated. The number is 1, but this one is less than 0.5, it's not correctly estimated. The number is 0, and this one is below the 0.5, correctly estimated. The number is 1, but this number is below the cutoff point of 0.5, not correctly estimated, right? Next, the number is 0, and this one is less than 0.5, then this is correctly estimated, right? So what this R square is basically gonna do is it's gonna count how many correctly estimated. It's 3 out of the 5 are correctly estimated, right? 1, 2, 3. Okay, I just want to make sure that this one is clean because this one is 1, less than 0.5, not correctly estimated. So how many correctly estimated? 1, 2, 3, 3 out of 5, or 0.6. The count R square is equal to 60%. So it keeps counting how many times the observation is correctly estimated. Okay, so I'm going to stop here, and what you can do is you can go ahead and watch my videos for the binary, like if I were you, like try to help yourself and help me. Binary dependent variable parts 1, 2, 3, 4. I have 4 videos on this topic. The only thing that you will be missing, or you can skip for now, is I'm going to explain these 2, or actually I'm going to explain like those 3 on Tuesday next week. But other than that, you should be fine. Also watch the video, the Stata video, which is in part 4. Okay, and then you have the materials for tomorrow's recitation, and I will also make sure that you have the materials of the last recitation. Any question? Fine. I will be available for virtual office hours, 15 minutes, about 20 minutes from now, which is, I'm gonna start at 1:15. I don't see anybody has scheduled to for the meeting, but if you have any question, I'll be there. And also, yeah, if you have any, Kasim is going to also hold virtual office hours, okay? So he will be sending you soon. All right, everybody, stay safe and stay well and take care. And I'll see you on Tuesday. Okay. Thanks. See you. Okay, bye.